I'm gonna leave before that.
I don't know what you're talking about, but if you factor an x times that 8x, I get a minus.
Okay.
Yeah, y'all can say. Thank you.
Okay.
And it's not ladylike.
Thank you. Okay? So, let's look at this equation. The factoring seems to be something that we moved through pretty quickly, which is great, but we've got to remember, guys, we're forgetting, not all of us, but some of us are forgetting key mathematical concepts when we go to solve this. When I ask you, what are the solutions? What does that mean?
What makes it?
Say it louder, David.
What makes it?
You got to be thinking about, hey, if I want a solution to this equation, I got to know what makes this equation true. The whole point of solving is to find what makes the equation true. Remember, we also talked about, what's another word that we regularly use for these types of functions? We talk about solutions, we talk about zeros. We also talk about roots. They're all connected, guys, right? So pause for a second. We're going to get to that second bell ringer. I do want y'all to pay attention to this discussion because we're missing some important details. We want solutions, and they're called zeros because what are we substituting in for f of x? Zero. And they're called roots because what point has a y value of 0? What point is going to... Say again. The what? The x-intercept, which remember how the x-intercept was r1 comma 0, right? Or in r2 comma 0. So remember, all of these ideas are connected. And so when we started here, I saw a great level of success around the room of doing a times c. What are factors of 64 that add up to 16? 8 and 8. Stop me if you got lost at any of these places, but I believe that we got through this pretty well. The only factor of x squared and 8x is x, and so what am I left with when I factor that x out? X plus 8 plus, what's here? Plus 8. Factor that out, and I'm left with x plus 8. And then what do we have in common? And I factor that out, and I'm left with x plus 8. Now, I want to point this out for all of you because this is a key idea that a lot of us forget. I know, legitimately, this has taken us longer to learn than I intended for it to take. However, it doesn't matter where you are. I want you to seriously reflect and ask yourself, do you understand this better than when we started at the beginning of this unit? And the reason I bring that up is I want you to always remember that you are capable. It's not just me asking you to say that. I'm not saying that everyone learns at the same level. Some people learned it super quickly in a couple days. Some of us it took longer. But with hard work pays off. You are capable of growing and learning because of a concept called neuroplasticity. I haven't used that word in a hot minute. But what that is a science. I know it's a crazy word. But all that we mean by neuroplasticity is that your brain can grow and develop. The more you struggle with things, the more you practice things, you're going to build what are called synapses in your brain. The more synapses you have, the quicker your brain moves. We're learning how to learn, and we're learning how to think, and we're learning how to grow. Okay? So we gotta keep working at it, keep practicing. If you're not 100% comfortable with this yet, then that's okay. Now, at this point, we've got a factored form. We've got a product equal to 0. So what key concept are we going to use? Now, I want to point this out. Do I need to set both x plus 8 equal to 0? Just to think about it, do I need to? I mean, what am I going to get for both of those, though? I'm going to get negative 8. So I don't have to set them both equal to 0 unless they're two different factors. X is going to equal negative 8. But I do want you to think about this, and I want you to remember, we actually talked about a problem like this yesterday. What is this parabola? What do we know about this parabola when I go to graph it? Good thinking? Not quite. We're going to have something a little funky with this. Remember, to have imaginary x-intercepts, that means I would not have real solutions. Do I have a real solution? Yes. So, when I look at the x-axis, what point am I going to have on the x-axis? -8, 0. But remember, it's going to be exactly that same point for my second x-intercept, which means I only have one x-intercept. So what point is that on the parabola? It's the vertex. If that's the only x-intercept that I have, it's going to look roughly like this. It's going to, talked about it yesterday, it's called a double root when that vertex is right there on the x-axis. And so these are things to pay attention to. It's not just random, right? We are finding solutions, we're finding zeros, we're finding roots, but by also finding out this information, I have key details to be able to sketch a quick graph. Why did I make sure this parabola went up instead of down?
A is positive.
A is positive, so I know the parabola is concave up. I have one other key point, really quickly, just looking at this graph, it's too big for me to write out, but when I look at the standard form, what other key detail do I know about this parabola? The y-intercept is 0, 64, so that's going to be way up here. Okay? These are things that we would want to notice, right? You can sketch a quick graph off of these features, off of the factoring, off of the vertex form, things like that. All right, there's that problem. The second one was actually first, questions, comments, concerns before we move to I. So that was equation N. Okay, so equation I was, what was it, 2x squared equals 15? Oh, by the way, I didn't need to mention this. Did I tell you what method to use on solving this equation? Did I? No. Most of us went to factoring, right? Because there were factors of A times C that added up to B. But could I have used vertex form here? How would I have calculated H in this case?
-16.
So negative B divided by 2A equals negative 16 divided by 2 times, which would give me a -8. Notice how that vertex value was the same as the roots because the vertex was on the x-axis. So, would vertex form have been a good option here? Yes? Could I have used the quadratic formula here? Right? Hear me clearly on this. On your assessments, you're going to have flexibility to choose which method you want to use. And so, if you identify, hey, Mr. Kenny, I can use any method on that equation, I just like this one because it's efficient, I know how to do it well, that's really strong understanding. But think through the things of which method can I use. All right? Now, when I look at this equation, what's the first thing I need to do? Subtract 15. Now, if I'm going to use the vertex form, do I need to subtract 15 from both sides?
No.
No, we talked about that yesterday. But if I want to use factoring, what's the end goal with factoring? We want to use what key property? Zero product property. If I want a zero product property, that equation has to equal 0. So, boom. To use the quadratic formula, what does your equation have to equal? 0. So if you want to factor, if you want to use quadratic formula, the equation has to equal 0. Don't forget that. So, we could have tried to factor right or use vertex form right away, but I will point this out. The fact that this is odd immediately tells me that I don't want to use vertex form. Negative b divided by 2a. What's the opposite of negative 7? Positive 7 divided by, notice how we're always dividing by a 2? So we want an even number with that b value, and we even get 2 divided by 2. That's a quick hint to me of, I don't want to do vertex. Can you? Yes. Because you have calculators, it can make it work. I just wouldn't. So, thinking through all those things, AC method of factoring, 2 times negative 15 is negative 30. Factors in negative 30 that add up to negative 7.
Negative 10 and positive 3.
Negative 10 and what?
Positive 3.
Positive 3. I do want to point this out to you, 2 things with this factoring. First off, is it possible that you miss the factors of A times C that add up to B. So do we just quit on this problem if we miss that? No, Nisha, what do we do instead?
Use a different method.
Use a different method, right? What's the method you can always use?
Quadratic.
Quadratic formula, right? Make sure you know that equation. Study it. Okay, so you can always do that, but I will also point out, because I have had a student who's been struggling with identifying the factors, you can use your calculator. For instance, when I look at negative 30, I could always divide by 1. If I divide negative 30 by 1, what do I get? Negative 30. Then I would pick up a calculator. If I take negative 30 and I divide it by 2, what do I get? Negative 15. Do either of those add up to negative 7? No. Then I pick up the calculator again. That doesn't work, and so I divide by 3. And I get negative 10. Does that add up to negative 7? So like, here's the thing, guys. You don't have to know the factors off the top of your head. Is it easier if you just immediately see the factors? Yes. But that calculator can be your best friend. All right? So, 2x squared minus 10x plus 3x minus 15 equals 0. Greatest common factor here. What can I divide both of those terms by? 2 and x. And I'm left with?
X minus 5.
Minus 5. 3x minus 15. What do they both have?
Plus 3x minus 5.
So I'm left with x minus 5. And do I have a common binomial here?
Yes.
Yeah. So I'm going to factor out my x minus 5. I am left with
2x plus 3.
2x plus 3. And that's equal to 0. Now remember, you cannot go from this equation to the two equations. You have to have a product so that you can apply the zero product property. I've only been showing the work here, but on assessments, to show that you truly understand the zero product property, I would want to see a note of, hey, this is a product of 0, meaning we're getting, what's happening? We are, what's that product word mean? We're multiplying and getting a,
0.
okay, so if we have a product of 0, we can use zero product property. That's the whole point of it, right? I want to see that you're thinking through and understanding, hey, that's a product of 0. I'm going to use the zero product property. So that's what I would be looking for. Now, I'm going to jump to the end here, but use your inverses to solve these equations. So in case you were working on it, there's those checks for yourself. What questions do you have about these factoring problems before we continue with today? Yeah, it's like, I'm crushing it, Mr. Kenny, I'm good. I got no questions. Is that right? Okay, is that what that look is? Good. All right, quickly with agenda. I should have put this note at the beginning. I know that I said we're going to have an understanding check today. I was reflecting on it though, and the understanding check needs to cover imaginary numbers, and we're not ready for that. We need to finish imaginary numbers today. We will have an understanding check on Wednesday, since I will not see you Tuesday, before you go to field day, so be aware of that. That means we're going to review on Thursday, test on Friday. All right? Now, hear me very clearly on this. What's your question, Mickey? Okay. You know you're out on Monday, right? And then Tuesday is ACT for juniors, and then Wednesday's field day, so we'll just do it before field day. So here's what I need you to hear me very clearly on. We need to practice. Another motivation for why I am doing the understanding check on Wednesday next week is I recognize that the internet was down all of yesterday. Because the internet was down, that means those of y'all who cannot do math yet at home weren't able to do it during enrichment. Okay? Get your math yet done today. Today is the last day that you can finish it without a penalty. Okay? So for those of y'all who have not been able to do Mathia because you don't have access at home, one, I will point out you can do it on your phone, it's just not as easy. But use your iPad. If you see the Barracuda message, log in using your TCSS login information. So remember, we're not here to just magically learn equations that you'll never see again for the rest of your lives. Why are we here? To be able to conduct arguments, right? We need to be able to look at the equation and make a claim about which method we're going to use. But we don't just randomly choose methods. We need what with that method? We need claims, and we need what for those claims? Evidence. Right? Okay, sorry, Preston, I'm talking over you. But we need evidence for our claims, guys. The point of an argument is not to just tell someone they're wrong. It's actually when we have a good argument with someone, that doesn't mean anyone gets angry. It means that we talk through, we make claims, and then we provide evidence for those claims. And then if our evidence is faulty, then the other person makes a different claim and pushes back on your claims and provides evidence. And by talking your ideas out, you're going to come to the best approach, the best solution, the best understanding. Argumentation and the ability to listen to other people's claims and evaluate your own understanding and either stick by what you believe or reevaluate and change, that is a skill that you should have for the rest of your lives. That's how you're going to continue to grow, continue to learn, and be a significantly better person. You are capable of amazing things, but we've got to grow, we've got to learn to do that. We're going to do a little bit more solving quadratic equations practice before we get back to the book to talk about imaginary solutions. So here's what I want us to do. We just did factoring for a couple. I want you to, whichever quadratic equation, whichever quadratic equation you did not use yesterday, or if you want to just find a different equation to do the quadratic formula with, you as a small group pick a equation. That's not right. An equation from the graphic organizer, any equation you want, and practice using the quadratic formula with it. After you finish that problem with the quadratic formula, move on to you picking an equation to use with the vertex form. Okay? So, let's get up, let's move to our vertical surfaces, and let's work on using the quadratic formula, using the vertex form to solve a quadratic equation. Two back to back, let's go. I'm going to be evaluating and giving you feedback. Come on, let's get up, let's move, let's go. Group 7, come on. Come on, group 7.
Why are we not doing this before school? Okay, that's more valid. Fair enough. Yeah.
Help make sure that you develop a better understanding. Amen. So first things first, when we use the quadratic formula, we need to be careful and make sure we're substituting everything in correctly. In first block, Naisha and her group had the wrong solutions because they substituted everything in, not everything, they substituted one thing in incorrectly. And so if this group had substituted one thing in incorrectly, I would not know for sure that they know how to use the quadratic formula. But what Naisha and her group had done, and this would be helpful on an assessment, is they wrote out the formula. And they wrote it out correctly. And on top of that, they said, hey, A would equal 4, B would equal -7, and C would equal -2. They have identified everything that they need for the quadratic formula. So when they substituted in, I could clearly say, hey, they just made a small mistake. Show me your quadratic formula. Show me identifying A, B, and C to make sure that we do not lose out on important credit just because we're being silly. That's a silly reason to lose credit, right? So show me your formula, show me identifying those values. Now, with this work right here, I want to talk about something because when I came over to this group, they simplified, what is this thing underneath the radical called again? Radicand, right? That's the radicand. They simplified it, they got the square root of 81, and then they took the square root of 81 and they got 9, but they wrote the square root of 9. Hey, listen, once you take the square root, then the square root goes away. Once you take the square root, that's when the square root goes away. Otherwise, the square root stays. But the square root of 81 is 9. There we go. Right? Square root of 9. And so then we can simplify this by doing -7 plus 9 is 2 divided by 8. And -7 minus 9 is -16 divided by 8. And there's my solutions. Actually, really quickly, Nicole, can you make sure that camera is focused right here because we need to talk about this method, right? So, please understand, with the quadratic formula, as long as you know how to simplify in, most of us are doing well here. I'm going to talk about one other small detail in a second, but I need us to look at this problem. I'm going to write some of this a little bit bigger. Here's the thing. they are showing me a really good start. It's going to earn some evidence of understanding on the rubric. But when we write this formula out, right, we should know, hey, A equals -1. You need to write A equals -1. Now I need H. They wrote out the negative B divided by 2A beautifully. They wrote out the -4 divided by 2 times -1, and they got an H of 2. They also correctly identified the K by doing, or at least eventually, making sure that we put the negative, notice that negative is not inside the square. -2 squared plus 4 times 2 plus 13. This is actually a mistake several groups made. Make sure that we do not drop off that negative, make sure it carries over, and then we get 17. And they had to correct some things, but I want to talk about this right here. This equation, or this vertex form, is not correct. But I need to talk more about what they did from here. And we need to learn from this error. It's okay to make errors, it's good to make errors. We just don't want to stay in that error, we want to learn from it. They did this. There's multiple errors in this. What is it? What are they? I'm going to let Kennedy talk first because she did have her hand up, then Kamara, you can answer.
The -1 outside of the parentheses, that's the and also the
So you're talking about using your inverses, right? But they did a square root, that is an inverse. So what's the problem with doing the square root right there? Kamara, you had your hand up earlier, and then I'll get to Shatiri and Nicole.
When you take square root, they cancel out.
Okay, yes, eventually, but that's not the error right now with that square root. Shatiria? Okay. So the square root's only going to undo the square, not that multiplication. So I shouldn't be doing the square root yet. There's other issues. Nicole?
It's not the last operation.
So one of the major problems is the square is not the last operation. There's multiple other operations to take care of first. But here's a big thing I need y'all to pay attention to, guys. The properties of equality to make equivalent equations tell us that what I do to one side of the equation,
You have to do the other.
did they take the square root of both sides?
No.
No. They didn't take the square root of the right-hand side of that equation. And in fact, they didn't even take the square root of the left-hand side correctly. We need to be careful about this. If I'm taking the square root of the left-hand side, I actually have to take the square root of the entire side altogether. That's why that's not the inverse I want right now. The square root's only going to cancel out the square. So we need to learn from this. Now, this group did realize just before we were going to switch that this should have been a 17. So what is, and remember, I think it was Nicole brought up the idea of the last operation being done. Is that right? Okay. What's the last operation being done in the equation? The plus 17, right? When I look here, it's -2 first, squared second, negative, multiplying by -1/3, following the order of operations. The last thing is adding 17. So we subtract 17. So I'm taking care of that. So -1 times x minus 2 squared equals -17. And last operation now.
1. Oh yeah.
The multiplication by -1. And someone did bring up, well, Mr. Kinney, it's a 1, I didn't think I have to write it. And I get that thinking, but remember, -1 is the opposite of 1. It's not exactly the same as 1. I need that to be a positive 1. So I'm going to use my reciprocal to create a positive 1. I'm left with x minus 2 squared equals a positive 17. Now the square is the last operation. Now the square root makes sense. So I take the square root to cancel out the square, and x minus 2 equals a positive or negative square root of 17. Then I add 2. And is it okay for a square root to be in that final answer? Yes. Can I take the square root of 17 easily and get a rational number? So am I going to take the square root? No. I took the square root here because the square root of 81 is 9. That's nice and rational. It's an integer. If I can't take the square root, I leave it like that. Unless I can simplify it. We'll talk about that some more today. So, What are your questions about the corrections and understanding how to use that vertex form? So please note it's not just about getting the answer, it's about understanding how to get there so that you can do it again in the future. Skylar, you got something you need to share with the class? Okay. I need y'all to also pay attention to this and remember, when we are factoring, we're trying to use what key property? Zero product property. But when I get the vertex form, the goal with vertex form is to use what?
Oh, yeah, probably.
Properties of equality based on the inverses, right? That's the goal. Don't ever forget that. Now, okay, I'll talk about this in a second. Really quickly, actually we're doing okay here. Notice they converted to h and k. They got h of -2, k of 14. There is one small mistake though that I will point out. No, you'll start on the inverses, I get that. But I want you to look at the vertex form again. And this is again why I want you to write out that vertex form. Here's my h. Here's my k. It's supposed to be what?
It's supposed to be plus 2.
Notice when we write that out, it helps us remember, don't we always need the opposite here? So if h is a -2, I need a +2. Be careful about that, guys. Please understand, is this showing me the majority of understanding and going to earn the majority of the credit if they continue solving correctly? Yes. However, those small details matter for getting the final correct solution. Okay? Nicole, can you zoom in over here? Here's what I want to talk about with this. Okay? So, with this, I'll go ahead and tell you, this is okay. You can just turn the swivel, right?
Oh, right here?
Yeah.
Oh.
So you can, if you loosen up the handle,
Right.
so turn it one another directions.
What hand?
So you
Oh, right
twist
here?
twist it.
I ain't thinking.
I'm going to teach y'all how to do this.
Yeah.
Okay, we'll just focus right here for now. So I want to point this out, right? We substituted in, we got our equation. Notice how we have the x equals out in front. The whole point of solving is to find out what x equals. So you got to have the value of x right there. The value of x right here. From this point, I do want y'all to notice this -13 plus or minus the square root of 41. When I look at the square root of 41, do I know what that is? Is that an easy thing to figure out? Then don't worry about it. When I look at 41, the only factors of 41 are 1 and 41. That's it. There's nothing there to really take the square root of except for 1, so I'm going to leave it alone. But I do, and so we see that across the board. One thing I do want to point out that is important here is to remember, because I see a lot of us putting our fraction bar just here. But this is saying that I'm only dividing the radicand by this 4. The entire thing is being divided by 4. Be careful and extend that fraction bar all the way across, because you actually need to do everything up here first before you divide by 4. And so we would leave it here. There are times when you will not leave it right there, and that would be in a case like this. If I had the square root of, say, 72, what is a factor of 72 that I can take the square root of? 7? Is that what you said? What's 72 divided by 7? Put that in the calculator.
9, 8.
Huh?
9, 8.
We all have calculators. Pick them up. What is 72 divided by 7?
72 divided by 7.
Yep, that's it. So it does not divide easily. Also, is 7 a perfect square? No. The perfect squares, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. Right? 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36. Are any of those factors of 72?
Nope.
Sure about that?
What about 8?
No,
Well, 8 squared is 64, right?
What? No,
Maybe just 3.
Say again? 3? What's 3 squared?
I don't trick. No,
I was saying, can I divide 72 by 9?
Yeah.
Oh, wait, I can. 72 is 9 times
8.
8, right? So can I take the square root of 9? Yes. But I will pause and I will point this out. When I look at 8, are there any other factors of 8 that I can take the square root of?
What do you mean? 4.
Can't I take the square root of 4? So when I look at the square root of 72, I'm actually going to rewrite this as the square root of 9 times the square root of 4 times 2. That is 72. But the beauty of this is that when a property of square roots is, I can actually rewrite this as 3 square roots. Square root of 9 times the square root of 4 times the square root of 2. What's the square root of 9?
3.
What's the square root of 4? And then I can't take the square root, so it stays the square root of 2. So this is just 6 square root of 2. That's a way to simplify that radical. You have to find perfect squares so that you can take a square root. Now, if you had something like this and you didn't simplify it, you have still shown me that you can solve a quadratic equation, but you have not shown me that you can simplify the radical. So you won't earn maximum credit, but you will still earn, you still show me the most important things. You're looking at 3's and 3 pluses if you justify this well and just don't simplify the radical. Okay? One thing I will point out about the 72 is, 72 is also 36 times 2. Can I take the square root of 36?
Yes.
So this would be the same thing as square root of 36 times the square root of 2. What's the square root of 36?
6.
Same or different? Same. So you can do it multiple ways. You just need to identify what those perfect squares are. Please pay attention to that. We're going to get some practice with that in just a second. I think that's all I wanted to address right now. Don't write this answer down. So, what are your questions about how to, the ideas behind using the quadratic formula and simplifying the radical and using the vertex form? Not just like the final answer, but making sense of how to do those things. Because I've addressed the mistakes that I've seen. We want to learn from those. Any questions about how to correct our errors? Okay. Get out your textbooks. M1 dash somewhere around 93, I think is where we are. Sorry, Nicole, can you actually put it back up here on the board? Actually, I can do that while y'all get the textbook out. You're good.
I'm already up there.
M1 dash 93, roughly. Should be seeing this page, I believe. Okay. So, I believe we started, I believe we started talking about this lesson 6 just a little bit. Please remember, the idea of solving quadratics is not changing. We're just learning about a new number that comes up when we solve quadratics sometimes. I believe we talked through these different quadratic functions on page 94 a little bit. So turn to page 94. We should have some notes, if I remember correctly, or did we not start on this at all? We started on it? Perfect. So here with f of x, we said that there are there's an x-intercept at -5, 0. Over here, I think we said the x-intercepts were 6, 0 and 0, 0. And here the x-intercepts were none. But a key idea that we talked about is that those x-intercepts connect to what other words? What other ideas that we talked about? So roots, we're going to talk about that idea in a second, but roots and zeros and solutions, right? But how many roots, how many solutions, how many zeros does every quadratic have?
2.
2. So when we looked here, we said that the roots, the zeros, the solutions were x equals -5. It was just that there were 2 of them. So we called it a what? Double root. That's why it touched the x-axis and bounced off, right? Over here, the roots were x equals 0 and x equals 6. So we already have our two roots. Notice those are just the x values of the x-intercepts. R1, 0 and R2, 0. But then right here we did not have an x-intercept. But there's still two what? Two roots or two zeros, we just don't know what they are. So we need to know how to find them. Okay? We don't know those zeros or roots. And so, looking here, how did we get through numbers 1 and 2? Does that sound right? We got through just number 1. We were kind of talking about number 2 and the bell caught us. So please do notice, right? What did Mark do wrong? We talked about this key idea that Mark is saying that there are these roots, which means we have these x-intercepts. 1, 0 and negative 1, 0. Does that parabola have those x-intercepts? No. Well, Mark must have made an error somewhere, right? We know, we've talked about this idea that those roots don't exist because that graph doesn't have the x-intercepts. If the graph has those roots, then we see those x-intercepts. And so we talked about Elena's solution. Does the solution fall within the real number system? Have we ever dealt with the square root of a negative before? Because here's the thing. Let's say I take 2 and I square it, what do I get? 4. If I take negative 2 and I square it, what do I get? Which means, and that's why when we talk about the square root of 4, when we are solving an equation and we take the square root of 4, we get either a positive or a negative 2, right? Okay. Now, technically the square root of 4 on its own is just 2, but when we take the square root, we get that positive or negative. So, to say that we have the square root of a negative 1, and we want to know what does that equal, what we're implying is that something squared is equal to negative 1. What number have you studied that when you square it gives you a negative? We haven't. All of the real numbers, every positive number, every negative number you've ever studied, when it is squared gives you a positive. So does the solution fall within the real number system? No. Nothing squared. Actually, let's clarify that. Nothing we know yet squared yields a negative. Right? So we don't know the square root of a negative.
Martin, can you move your head?
I'll read it as well. No, nothing we know yet squared yields a negative. So we don't know the square root of a negative. The whole idea is that we don't know anything squared to get a negative. So we don't know that square root yet.
Start moving your head.
So once again, because we've written this down, right?
Can you put tall people in the bed?
I don't know what you just said.
Can you put tall people in the bed?
I still don't know what you said.
Can you put the tall people in the bed?
Lucian!
We can say it more respectfully. Nothing we know yet squared yields a negative, so we don't know the square root of a negative. So are you listening when I read it out?
Brooke was talking.
Nothing we know yet squared yields a negative, so we don't know the square root of a negative. The reality is everyone makes a better door than window, so you can't really see through a person no matter what. You never heard about it. My dad used to say it all the time. I thought it was weird, but
Who's your
no.
dad?
Ted Kenny.
You said Ted?
Daddy, Ted.
My
Daddy.
I mean, it's a normal.
I would say his name's Theodore William Kenny. Well, he's a junior, and he goes by Ted. So, we did not get here if I remember correctly. Number 3, I think we didn't even start talking about it. So here's the thing. We are looking at this idea that we need something squared to get a -1. So mathematicians said, well, you know what? I don't have anything squared to equal -1, so I'm going to make a number. And they created the number I, such that I squared is equal to -1. Right? Mathematicians defined a number because we didn't know the number, so that I squared is -1. This is on the next page. You need to know this fact. I squared is -1. So, it's an I. We traditionally, especially when writing it, put the little hook on it to indicate. Notice how they italicize it here. This is like italicizing it when you write. That is to make sure we don't mistake it for other symbols. Okay? That's why we use the I, like that. Okay? But if I squared is -1, right? They have defined a number so that when we square it, we get a negative. What is just I on its own?
-1.
Positive
1. 0.
It's not existent.
That's not existent. So I want you to think about this. If I say that I is a 1, that means that when I square 1, I get -1. Is that true?
Oh.
Nope. If I put a 0, 0 squared is 0. Think about this, guys. How would I go from I squared to I? Square root, right? So what is I? Square root of what? That is the definition of I. If I squared is -1, by definition, I is the square root of -1. I is the definition, huh? I mean, if I squared is -1, so I will remind you, right? We have no number in the real number system, so that when we square, we get a negative. So we defined a number I standing for imaginary. We've defined a new number so that I is equal to the square root of -1. And here is part of how it makes sense. Look, if I square the left-hand side, and I square the right-hand side, what's the square root squared? What do they do to each other? Right? So if I square I, what do I get?
I.
-1. Remember, I is the square root of -1. I squared is -1. So I is the square root of -1. I squared is -1.
What's one of I? That's a J.
Okay, first off, J knows this direction. Second off, that's how you would italicize an I when writing by hand. Notice how the number I right here is italicized. You can't really italicize, but that's how we would indicate it writing by hand.
It's kind of like a
So,
Yes?
so you put the square root of -1 into the calculator, it says a non-real calculation.
Yeah, because the square root of -1 is what kind of number? An imaginary number.
So-
But, watch by hand. And there is a way to make the calculators give you the eyes. But here's what you would want to recognize, right? So let's say that I have the square root of -9. You remember earlier when I was talking about simplifying those square roots? I can do the same thing here. I know that I is the square root of what? -1. So I could rewrite -9 as -1 times.
So that's not true at all.
Hold on.
Negative
-9.
Delusional.
-9 is -1 times 9, right? And remember how I talked about, okay, I can split it up. When I'm multiplying like this, I can rewrite it as square root of -1 times the square root of, not -9.
Well, where did you get the -1 from?
Where did I get what from?
The -1 from and add it to the 9.
And I added, remember, that's a -9, right? -9 is the same thing as -1 times 9. Okay? So I rewrite it like this. Now, what is the square root of -1 by definition? I. What is the square root of 9?
3.
So the square root of -9 is the same thing as 3i. That's it.
Oh,
That's it.
oh.
And you can start to jump in a second, but if I look at the square root of negative 16, I don't know the square root of a negative yet. But when I think about this, I can rewrite the square root of negative 16 as negative 1 times what? Times 16, right? So that would be the square root of negative 1 times the square root of 16. What's the square root of negative 1? I. What's the square root of 16? 4. So the square root of negative 16 is the same as 4i. That's it.
Well, that's simple.
It ain't bad if we understand how to simplify those radicals.
I like I.
It's not terrible. It sounds crazy because like, well, Mr. Kinney is imaginary. It doesn't really exist, but it does. It's just we didn't think it did at first.
What's the next letter we learning about?
Nothing right now. We will.
You trolling at this point.
Before, I don't know if we'll get there before you leave, but we will study the number e. Yes. So here's what I want to point out. Remember how nothing squared before gave us a negative number? By doing 5i and squaring it, I can get a negative. Because that is 5i times 5i. What is 5 times 5?
25.
And what's I times I?
25. Oh, negative 2.
I squared. And what is I squared? Someone started to say it.
1.
That's 25 times negative 1 then, which is negative 25. By introducing the number I, now when I square something, I can get a negative. That's the whole point of the imaginary numbers, is that when I now square an imaginary number, I can get a negative. So 5i squared. So this is the point.
Mr. Kenny, you remember when you told me we was going to do this whole group?
I was going to try. Point of imaginary numbers is that a number squared can now be negative. So the point of the imaginary number is now when you square I, you can get a negative. So make sure we have that detail down, that the point of imaginary numbers is that a number squared can now be negative. Say it again. Yeah, you can put it under 3. There's a lot of space under 4, and 4 won't take long, so you can also put that under 4. So the point of imaginary numbers is that a number squared can now be negative. And notice I showed that word to show an example of that, where 5i squared comes out to be a negative 25. Okay. Make sure you have this idea down. And now let's talk quickly about number 4. Number 4 says, recall the function p of x equals x squared plus 1. Write the zeros in terms of I. So if I'm looking for a 0 or a root, that means that my y value is what? If I'm looking for a 0, the y value is 0. So 0 is equal to x squared plus 1. Elaine already did this work, but how would I solve for x in this equation? Brooks, you focus up here? How would I solve for x in this equation? Kennedy?
Are you guys talking about what's the next step?
Yeah.
Minus.
Shatira, you had your hand raised. Is that what you're thinking? Minus 1? Yeah? Okay. If I subtract 1, is that going to get me closer to figuring out what x is? Negative 1 is equal to x squared. Now what would I do?
Oh. Square root.
Square them both?
Oh no, I meant square root. So negative 1 and
Okay, so square root, because that's the inverse of a square. Okay? And so what is the square root of negative 1? I. And so, don't forget I need 2, right? Positive and negative I. The square root of negative 1 is I. That's the whole point, is now I can deal with imaginary numbers. The square root of negative 1 is I. So I solve it, like normal. This is no different than what we did before. It's just now when I get the square root of a negative, I know I need the number I. That's the only new thing here. When I get the square root of a negative, I need the number I. Now, number 5, in the detail just above it, functions and equations that have solutions or zeros or roots that require I have imaginary zeros or imaginary roots. And so how can you tell from the graph if there are real solutions or if there are imaginary solutions? Why did this function have imaginary roots? What was the issue? Shateria? There were no x-intercepts. Remember, the x-intercepts, the x-axis is all of what type of numbers? What type of numbers are on the x-axis? Real numbers, right? So if there are real solutions, the graph has to intersect the x-axis. So when do we see real solutions? The parabola, what? There we go, intersects the x-axis. Yes, like the first two problems. So when am I going to have imaginary solutions? Here we go. Now, because of this, with number 6, can you determine the imaginary solutions by just looking at the graph?
No.
Remember, with the real solutions, I could look where to find those roots at the x-intercepts, the x-axis, right? I can't do that here. So can I see imaginary solutions on the graph of this function? The x-intercepts showed the real roots. But there are no x-intercepts for imaginary ones. Right? The x-intercepts showed the real roots, but there are no x-intercepts for your imaginary roots. The x-intercepts showed the real roots, but there are no x-intercepts for imaginary roots. That's important. Now, does that mean we just give up and we don't look for the roots?
Yes.
No! It just means we have to solve it algebraically. We cannot do it graphically, we have to do it algebraically. And so what I need you to do is turn to page 106. And we're just going to look at a very, very brief introduction on 106. And we're only going to look here at f of x for now. F of x is a parabola, it's a quadratic. We'll talk more about this on Monday, or Wednesday. We have a vertex and y-intercept of 0, 9, and this parabola is going to look like this. Don't stress about graphing it right now, I just want to talk through this one. Looking at that parabola, how do I know it has imaginary solutions?
Because it don't go across the x-intercept.
So it does not intersect the x-axis, so it doesn't have x-intercepts. It's small, but it's an important difference in language, right? The x-intercepts are where the graph intersects the x-axis. But I can still find the roots, which is what number 3 is really starting us on. Okay? Number 3 is really looking at this idea. We'll come back to a lot of this. But if I want to look at this equation, right? And I'm looking at f of x, and I want zeros. How would I find the zeros for this function?
By finding the x-intercept.
Okay, but remember there are no x-intercepts if they're imaginary roots.
Find
Remember,
the root,
if zeros, why are they called zeros?
if they imaginary.
No, we can have real zeros.
So double root.
The y is what? 0. It's called a 0 because the y value is 0. What would I now do to solve that equation? Subtract 9. 9 minus 9 is? And so I'm left with negative 9 equals x squared. Remember before, did anything squared equal to negative? No. But now I have a number squared that equals a negative. What would I do to solve this equation and not pack up because we're paying attention to Mr. Kenny teaching? What am I going to do? Square root.
I need these students to come see me.
Well, you can start to jump. What's the square root of 9?
Jaden Jones.
3.
That's it, thanks.
What's the square root of negative 1?
Not
I. X is equal to plus or minus or positive negative 3i. Now you can take the longer route. That's the square root of negative 1 times 9. Square root of negative 1 times the square root of 9. Square root of negative 1 is? I. We always write I second. Square root of 9 is 3. And that's why it's positive negative 3i. So we cannot find these graphically, but we can still use our inverses with properties of equality. You can still use the quadratic formula. Notice you can't factor because factoring has to have real roots. I will see you on Wednesday. I'll see you at prom more than likely as well. But make sure you finish up Mathia that you study for your midterms. Remember, you all capable of more. Yes, sir. That's right. What's up?
If you don't, I do know that. If y'all don't remember that,
Please no. Don't do that.
I said no.
Can you come back after third? Just about this third one.
there's no.
Okay.
I'll give you one.
You ain't gonna
I'll have
eat
you
it.
check out paper.
Izzy, I think you made it a little bit. You made a leg? You made it a little bit.
My bad.
CJ, is the factoring starting to make more sense?
Oh, so they still say.
I told you, it takes time. I get it. But you can do it. Don't give up on yourself. Because what are you, CJ? Capable. Yes, sir. Good morning, Ryder.
Come on.
Ben?
I'm good.
Yes, sir.
Can I?
Good morning, Trey.